record the meeting. Okay. Sorry about the delay again. Okay, everything's working. Yes, people are in the okay. Okay, so as I said, the last video, I think I uploaded it and it didn't upload correctly and I didn't notice, and then I took my computer to the shop because it made the weird mechanical noises. So once I'll have my laptop back, hopefully the video will be on there and I'll upload it. I do want to remind everyone, if you hadn't noticed, that there is in the TA drive session, folder, useful links. So this is a document that I put with all kinds of things that you can teach yourself. And also they're inside helpful stuff. Wait, I'll just share it. I put a new share this screen. I put a PDF file, an idiot guides to support vector machine, which I found very helpful. It goes through the math, the loss functions, the Lagrange multipliers, and everything. So I am not going to go through it with you guys. You guys are welcome to go through it alone and then ask me questions if you have any questions. Okay. Instead, we're going to be moving on to neural networks. However, right before we move on, I do want to wrap up support vector machines just so we'll have it recorded in case the other recording is lost. And also, I talked to Osnat and we feel like it's okay if you don't understand all the math behind support vector machines, SVMs, but you should know kind of what it does and how to use it, even in sklearn. And the big things that I want you guys to know, we'll write them down, are we said it looks for a best separator. So not only just any separator that can separate the data, but one which is best, which has the widest margins, remember? So it separator with widest margins is the best, right? So it's kind of a good improvement on what we've had before. It can handle non-linearity by using kernels. Kernel functions are kind of a way to project the data into higher dimensions or in different dimensions, and then have a linear separator in those other higher dimensions. And then that actually is a non-linear separator in our original dimension. And that's a good thing to remember. And then we can also have soft margins. So we can kind of relax the criterion that you have to have a perfect separator, that the data is perfectly separable, and still SVMs will work. Okay, so remember these three things. Remember, know how to use them, know how to use the code, and I think that's okay. You want to get into it deeper? I have the PDF file. Okay, we wrapped up SVMs. Awesome. Also, I'll just say, in case someone ever gets interested in that, they're supposed to be very efficient and quick. Okay, I'm not writing them. Second thing I want to correct is, remind me your name, please. Arna, you asked me last week about Laplace smoothing, and I was interested in what you said, and I think I read about it a little more, and I think you were right and I was wrong. So I want to correct the record and to explain what I learned about Laplace smoothing. So as we said, Laplace smoothing. When do we use Laplace smoothing? When we want to make sure that we don't have, when we have data which comes in probabilities. For example, in naive Bayes, we have kind of probabilities to see certain data in the class, but we don't want to have any probabilities of 0 and 1 because they kind of ruin our equation. If something is probability 1 or probability 0, then it can never occur. So we're gonna take 10 minutes. We're gonna explain Laplace smoothing, a little bit the intuition behind. I think it's good to know. Okay. It's not directly related to the course, but it's good to know. Let's say I ran a trial for a drug company, and I want to see if there are any severe side effects. And I tested, so I want to estimate what is the probability of a severe, so we'll call it P, which will be the probability of a severe side effect. Yeah, anywhere you want to use probabilities, it's good. So Laplace move. So let's say, what's the probability that my drug causes death, right? Or other side effect. Let's do side effect. I tested my drug on 300 people. None of them had a severe side effect. What should my estimate for P be? Should it be 0? Because 0 out of, right, that's naively. You'd say, oh, 0 people out of 300 had that side effect. So P should be 0. That's my best estimate, right? But we kind of feel intuitively that this is not really like the best estimator because my sample size is limited and all kinds of stuff. And because just because I hadn't observed that side effect doesn't mean that the probability of it is 0. To say something has a probability of 0 is absolutely means it will never ever happen, right? So, oh, and another thing that is a problem is that let's say someone else ran the trial with 3 million people, and they also saw 0 side effects. So they also estimate 0. So we both have the estimation of 0, but we kind of feel like their estimation is much like is better, right? They use like 3 million people and they didn't see. However, it is not reflected in our estimates. We both say 0, right? But their 0 should be like stronger. Okay, so for that trick, there's a Laplace smoothing. And Laplace smoothing, so we just essentially says this. Before you register any data, pretend that you saw one of each observation. So pretend that we saw one with no side effect, and then one with side effect, and then however many, 300 more with, that's the data after, with no side effect. Okay, so this is the pretending part that we pretend before we see the data. No, 300, because these two are not real observations. These are the ones we pretend, and these are the ones that we measure. This is our actual data. Okay? This, I'm calling them the pretend. Now, it should be clear that the probabilities will never be 0 now, because we always have at least a pretend one person, right? And then our actual estimate will be 1 person out of 302, right? So another way to say this is that we're adding the observed plus 1. Sorry, I should have wrote observed side effect. I'm going to delete this. We're doing the side effects observed plus the one that we pretended over all n plus the 2 that we pretended. Okay? And this was how I learned of Laplace smoothing. Another thing you will see is that if you work out, these will always sum up to 1, because we will have 1 over 302 with no with the side effect, and 300 plus 1 over 302 with no side effect, right? So it will always sum to 1. So I'm just going to write 300 and 1 over 302. Then I'm going to just make sure. Let's say this is Now the no side effect here. Side effect is here. And then they sum to 1. Let's do it nicely. We'll add plus equals 1. So this is how I learned about it. And that's why I said last week, it's you add 1 to the numerator and 2 to the denominator. However, let's say of a different case where it's not just we're checking if there's a side effect and no side effect, but we have a bag of words model with 11 words. Each one equal probabilities to come. So I'm sorry, it's not each one equal probabilities. We want to estimate the probability of each word for our different classes. So in one class, a certain word can have a high probability, in another class, a certain word can have a low probability. However, let's say in one class, one of the words, let's say word 1 for class 1 never appears. So we have a problem because again, what are we going to estimate at a 0 probability? But it's the same problem we had before. We don't want to put the 0 probability here. And also we only observed a finite amount of class 1 and so on. So what do? We start with pretending there's one of each class. So one observation for each word within each class. So 1 of word 1, and then 1 of word 2, and so on. And then we have the actual observations that we have. So we have, let's say, 3 more observations of word 1, and the whole point was that word 1 was not observed. No, this is the data that we pretend to see first. We first pretend to see 1 of each, and then this is the data that we actually have. So let's say we actually have 0 of word 1 and 3 of word 2, and so on. Oh, but let's make it interesting. Let's add word 3. No, let's say we have 11 words. Right, and so on for each, because I think that's what we talked about last week. So this is 11 pretends, right? And then each one, one observation of each. And then this is the actual how much we observed. I don't know how many words we observed, but like in all of our data set, right? It could be 3, let's say again, we observed 300 words for that class, okay? Excellent. Now the probability of word 1 will be equal to 0 observations in the data, but the actual 1 pretend observation for word 1 over 300 plus 11, because we have the 11 pretend observations. Okay? Yeah, we had the 300 actual data words that we have. I'll write this, the 300 words in the data. Okay? And then the probability of word 2 will be, so for word 2, will be equal to, we have 3 actual observations plus that 1 pretend observation over 311. So it will be 3 plus 1 over 300 plus 11. Okay? And in the general case, okay, so the probability, the Laplace smooth probability, including adding the pretend for every outcome, will be the observed plus 1 over all of n plus k, where k is the number of different outcomes that we have. So in the no side effect, we only had 2 outcomes. That's why it was 2. But in the bag of words model, we can have 11 different outcomes because we have 11 different words which can come. And if we do the math, we see that if we do this one for each one of the 11 words and sum all of them, they will also sum up to 1, just like what we had here. Okay, so this is the good Laplace smoothing. And this is the one I want you guys to remember. Questions about that? Yes, in this case. In this, let's do it in red. I like this.
So to be clear, this is the probability of seeing word one if it's class.
Yes, inside a class. You do it separately for each class because you want to estimate the P for each one of the classes, for every word for each one of the classes separately. Because we are actually building two distributions, one for each class. Remember, it's a generative model that we build two distributions, one for each class, and then we see an observation and we see based on this class, what is the likelihood of this, and based on this class, what is the likelihood, and we see which one is higher.
But it's not the probability that this is class one, given we saw word one.
It is the opposite. It's the probability that this is word one, given we're in class one. Yes, exactly. It's very confusing, I know, but I think we ran through it. And in any case, whenever you have questions, come to me. Okay.
Ask something.
Yes.
You have a word that is present in spam but is not present in pump, for example.
Yes.
Like I feel like I would still wanna add a pseudo count both spam and pump because otherwise one would be probability 0.
So this is exactly what we're doing. You're adding a pretend count for both inside spam. Yeah. So this is all inside spam. And then you do it separately inside ham. So within each class, you add the 11 pretends or the 5 pretends or how many pretends you wanted to.
So like here we are adding word one because in the other category it was present, but not here.
Yeah, so the bag of words model, you have to say which words are in the bag, right? You can also say there are 700 words in the bag, and then you add 700 fake observations for each one of the words.
Yeah.
Right? So I don't know what the question said, how many words are inside your bag, but I assumed it's 11 because those are the words we want.
The bag of words is shared between the categories.
Yeah, I think that's what the question was asking. If not, I wonder if you can do, because what happens if you see a word which is only in one category? It's like saying it's 100% that we're in that class. Yeah. So, but you say, oh, I want to add a non-zero, but a small but non-zero percent in the other class. So then the bag of words is shared. Yes, I agree.
The probability is not shared.
The probability is not shared. If the same probability was for both classes, then that word doesn't give me any information about which class I am in. Excellent. Okay. I like this. I like this. I like that we did this. We learned stuff.
So one more time, when we are comparing two classes, we will take whole bunch of words, not only each. For example, 10 in spam and 15 in ham. We take 25 for both of them.
Okay, so no. So you wanna first decide how big your bag of words is. You can use that based on all the words that you have in all of the classes. You can also add words that you didn't see in any of the classes, right? And then for each class, you make a pretend observation for each one of the words, plus the actual observations for that words in that class. And then you get your P estimates for each word within a class. You know what? I'll add this. Yeah, okay. Just so it's clear. I'll say that we did this for ham. Let's say for class 1. Why am I in red? You have to decide, first of all, on what your vocabulary. Vocab size equals 11. You decide it based on whatever considerations you have. And then for each class, you add 11 pretend observations, one of each word, okay? Is this clear? No, so we said we want a shared vocabulary, a shared bag of words. So yeah, but the P's will be different. The probabilities of each word will be different for every class. And that's how we will use these words to say which class we're in. Yeah, okay. I'm glad we did this. All right. Now, let's see what I write on my note. Yes, we're going to move on to neural nets, and we're just going to start with them. And we're going to continue on Tuesday, okay? And I think we can finish maybe even 5 minutes early, and you guys tell me if you have any questions about the homework and stuff. Okay. All right. Artificial neural networks. Loud sound. Is one of the worst names in the history of science and computers. It was given, that name was given because people back then believed that our neurons and neural networks in the brain work like that. Today, a lot of people still believe this, even some neuroscientists. It's a big debate in the field. To what extent do these artificial neural networks are similar, work the same way as our actual biological neural networks? However, it's very confusing because you say neural network and you don't know if you mean an artificial one or a biological one, especially when you're in the neuroscience building, right? Where we talk about both. So what I'm going to say is that I'm not going to be the one to fix the terminology. In this course, whenever I say neural networks, I mean the artificial ones, okay? But outside of this classroom, I will try to always refer to the artificial ones as ANNs, artificial neural networks, in order not to be confused. And I urge you guys to do the same, or at least clarify what you're talking about, okay? Someone tried to do the other way, it's called the biological neural networks, BNNs, and I don't like that name at all. I think it's annoying, BNN. Okay. So who remembers this picture from way back in whatever, how many weeks ago? This picture was a representation of a GLM. We said GLM, we do some linear combination of our features times the weights. Remember, we later rewrote this as the beta vector times the X vector, right? Or the beta transpose vector, right? And then we put it into some non-linear function, usually. Some non-linear function. Can you guys remember any? Which one? Logit, for example. Yes, another one. Yeah, sigmoid is the logit. Is the same. It's the inverse. Yeah. Softmax. We also used softmax when it was a multi. A simple, easier one for the perceptron, for example. No. Yes. It is no, sigmoid is the 1 over E, which gives you the probabilities. Sine, remember? If it's sine function, if it was positive, you go 1. If it's negative, you go -1. Remember? Or others. There can be others. We didn't talk about all of them. And then you get some outcome. And we said we can write the x's going downwards in circles, and then the betas, the weights in the lines, and then we do here it is, the beta transpose x. And then we get to some nonlinear function, we have a y. Okay? And for if we want to predict more than one y, we can go to let's say we want to predict the probabilities for 5 different classes, we can do this thing 5 times and have 5 y's. Remember that? Excellent. So now we're going to use this graph. Okay. We're going to use this graphical representation. I'm going to do something that will shock you, blow your minds. It's the first time you've seen it. I'm just going to say something about the beta 0. The beta 0 is called the bias. And it can be thought of that it's always multiplied by 1, right? So what I could have done is, is add another circle and always write 1 and do the beta 0 times that in order so it doesn't always like hang off the top. Okay, is that clear? And that's what we're going to do from now on. So I'm never going to draw the beta 0 again. I'm always going to assume that your first x is a 1. We can call it the x0 term or something like that. It will be 1 for all the features, for all of your data points, and it'll be multiplied by the bias, okay? Cool, so now what we're gonna do is we're gonna assume a different problem. Let's say we have 3 features. Let's say we have 2 features. We'll have the intercept, the bias term, and 2 features, okay? So what do we want to predict? Something based on 2 features. Something fun. Let's do the rat's ability to solve a maze, or the time we'll take it to solve a maze. So it's a regression problem because we're predicting a continuous thing at time. So time to solve maze based on x1 instead of equals. I'm doing based on x1, which will be the rat's brain size. Yeah, that's good. I like that. And we can do x2. It can be if the rat has a certain mutation. It can be a 1-hot encoded. Yeah, let's do x2 if the let's do it binary if the rat is mutated or not. Okay, based on x1 and x2 mutation. Has okay, and then so we will have our 1 feature, right? So what would we do? We would we'd choose. We want to do some GLM to predict it. We don't know which one, right? So because maybe it's a nonlinear relationship, we're gonna choose find the weights, find the parameters, right? We're gonna have 3 parameters, which will be multiplied by 1 times x1 and x2. We're going to have some nonlinear function and so on, and we can use gradient descent to solve for the optimal parameters, which will give us the lowest loss function and so on, right? This is all clear stuff. Okay, now I'm going to do something a little bit more complicated. x1, oh, no. Waiting to see what I'm doing. Just the 2-layer. Yeah. Everyone's excited? No. Okay. I'm going to use 3 different betas. I want this to be the as we know, so this will be beta 0, beta 1, beta 2, and then we're going to get here the combination beta times x, and we're going to get some number, and we're going to get a nonlinear function on that number, right? Same as we did. However, we're going to name these weights beta 0, 1, beta 1, 1, and beta 2, 1. And now we're going to do the same thing with 3 completely different weights, which will get to a second number. So this will be beta 0, 2. And this will be beta 1, 2. and this will be beta 2, 2. And they will come to a completely different, we'll write this beta, we'll do a completely different B transpose X and a nonlinear function. So essentially we did 2 linear combinations. So we get 2 outcomes, 1 for each linear combination. And now we take the outputs of these. And we add 2 more parameters. All this beta, let's call it beta 1, 1, 2, 1. 2 new parameters. So we're going to get a new, this will be beta times X, right? But this X, you know what? I don't want to call it X. We're going to call the outcome here Z1 and the outcome here Z2. And then here we get beta times Z. Okay, so it's not times the X's. And again, some nonlinear function. And this will be mapped up to our predicted Y. So what we did here, I did it graphically. Our predicted Y, Y hat or Y tag or whatever. What we did here, we essentially stacked the GLM, okay? However, there are a few things that need to be made clear. What is this? Yes. A few things that need to be made clear. One, our number of parameters is much larger. We have many more parameters now. We used to only have 3, right? The beta 0, beta 1, beta 2. Now we have 3 to map to Z1, 3 more to map to Z2, and 2 more to map from Z's to our Y. Okay? So it's 8, much, much larger. However, because we can allow these Z's to be whatever we want, we are not restricted to a linear combination or even the nonlinearity that we have. We can actually have much more complex interactions between the variables or interactions between the nonlinear functions that the overall mapping from our original X vector to Y can be highly nonlinear, can be very complex. We remember the term expressive. Expressive is how well can our function that we choose fit the data. So this can be very, very expressive. And if you don't think it's expressive enough, we can add more layers. We can keep doing it, right? We could have had, instead of 2 Z's, we could have had 200 Z's. And then we would have had 3 parameters for each Z, so 600 parameters. And then 200 more parameters mapping from the Z's to our Y, right? Yes. Yes, they're different. So now that was a good point, and that's what I wanted to talk about terminology, and then we're going to end there. I'm just going to say this is called a neural network. Okay, so it's just the GLM that we know, just stacked, many of them. But now we're going to be talking about terminology. So the first thing we need to talk about. The whole thing, the neural network, it has a name, the architecture. The architecture means from how many X's you start with and to how many Y's you get, right? But also what happens along the way, right? So here we have an I'd say each one of these steps or thing is called a layer. So this is our 0th layer, which is the input layer. And then this is our output layer, so we also don't count it. And in between, we have hidden layers, and in this case, only 1. So we call this layer 1. Okay? The architecture of the neural network specifies how many layers you have in between and how many connections you have. Okay, so we know what layers are, we know what architectures are. Now we're going to discuss the terminology for the betas. Okay, and then we're going to be done for today. And next week, we're going to learn a lot more. So I am using terminology. Okay, so the terminology will be this. Within each mapping, so from input layer to layer 1, each beta receives two numbers. The number of the neuron where it comes from. Oh, I also forgot to mention, these little things are called neurons, like the numbers that we get along the way, or units. The circles, yeah. So this is a neuron, which is a number that we measured, right? Because it's the X1 is the rat's brain size. But then this is a neuron, which is not a number that we measured. It's a number that is the linear combination of features times weights, right? And this is the output neuron. Okay, so you get two numbers for each weight, which is the neuron where it comes from and the neuron where it goes to. So this one comes from the 0th neuron in the layer before to the first neuron to the layer above. We should have probably done 0, 0. I don't like it. I like that 0 is only for the bias in the beginning. But it doesn't matter. Okay, you have to decide if you start counting at 0 or at 1. Okay, and then this line, let's do it in red, is B1, 2, because it starts from the first, the 1 neuron, X1, and goes to the 2 neuron. Okay? However, this is all between the input layer and layer 1, and then from layer 1 to layer 2, or to the output layer, it kind of resets. So you get new B11s, okay? So if you want to also specify where the B is in between the layers, you add a number above the B. So this will be 1. Let's do it in black. So this will be 1 above, meaning it's like in between the input layer and the layer 1, and this will be 2. Okay, so essentially, for all the parameters in your model, you need 3 numbers. The first number, which is on the top, we kind of write on the top, is from which layers it connects. And then the second 2 numbers are from which neuron in the previous layer to which neuron in the next layer. Okay? And I'm going to try to stick to that terminology. And then what we will see on Tuesday is how we convert all, just like how here we could have converted the betas and the x's to vectors and just done the vector multiplication to get a number. I'm sorry, the dot product to get a number. So here we will convert all the betas into a matrix, and then we will multiply our previous layer times the matrix to get our new layer. So it's all linear algebra. The non-linear activation functions, remember we called them the activation functions, right? They can be anything, and in general, you almost always choose them to be the same one for all of the neurons, sometimes except for the last one, the output. But you could choose them differently. You could have done, this is a sigmoid and this is the sign, right? You could have done it. The activation functions, remember that we have the non-linear activation functions between each neuron. So you could have said that the first one is sigmoid and the second one is the sine function, and then, right? But because in practice, we always choose them to be the same function, or almost always, I'm not giving specific indexes for them. But we could have said this is the activation function for the neuron, the first neuron in layer 1 and what it is, and this the activation function for the second neuron in layer 1, and so on, okay? But I'm not going to bother indexing the activation functions. Okay? Excellent. What else did I want to say about neural networks? Name, we treated this, layers, architecture. Oh, excellent. Okay. In the links that I sent you, there's a playlist of 4 videos or 3 videos. I think each one is 15 minutes long, maybe even shorter, by 3 blue, 1 brown. Great animations. I'm highly recommend you watch it before let's say Tuesday or before next week or so on. I think if you watch those videos, you won't really need my TAing or the lecture. Like he covers everything much better than me. I can't not recommend it. Okay. So go look for it. And that's it. Any questions? Yes.
What should stop me from using, like you said, 2 million betas for each layer?
Yeah, so you will have a lot more parameters. So there's a lot, you have to search for the best parameters. It's a much harder search, right? Because remember, because to search for the parameters, we do iterative ways like gradient descent, and these things can take time.
So yeah, so time and like
And
resources of the computer.
and the search space is really big. So you know, so you want to not get to that like you want to be able to search it efficiently and well, right? I will say we didn't talk about this, but neural networks are so expressive, like decision trees, that they tend to overfit. So we will talk about ways to combat overfitting. Don't worry, it's not any new ways that we didn't learn about. We just have to keep that in mind.
And the more betas I have each layer, and the more I am prone to overfitting.
Yes, because your expressiveness is bigger. Yes. Which is also true in decision trees. The more splits you're allowing yourself to make, the more you're prone to overfitting, and it's also true. Okay. Awesome. Thanks, guys. Hopefully that was recorded, and I will upload it.